So, very good morning to all of you. And in today's class, last time I just introduced you to some basic concepts of testability. Today we are going to learn something known as fault modeling. Okay. So, first of all, let's revisit these definitions. What is a defect? What is an error? And what is a fault? Okay, so defect in an electronic system is an unintended difference between the implemented hardware and its intended design. Like during fabrication, defects can crop in. Okay, like an unwanted short to wire or an open, like wire getting open, wire getting short. So it could be because of process defects. Okay, missing contact windows. That means you wanted to make an interconnection between two layers of metal, but that wire has not been fabricated properly, and hence they are not connected to each other. There could be some parasitic transistors which have been formed. Okay, there could be somewhere where the oxide has broken down, like the thickness of the right oxide, if you are fabricating an oxide thickness and it has not got uniformly deposited, and there is a hole in that, and above that you have put in metal, so that metal will go and touch the channel, right? So that the transistor could remain permanently on, or it could remain permanently off. So those kind of things can come. So they are known as the process defects, and there could be some material defects, like there could be some cracks in the wafer itself, right? Surface impurities can be there. And then once it is fabricated, packaging defect. So you got to finally package it, right? So during the package, if the connections from the die to the pins, if they are not proper, so those kind of defects also can come. And finally, there could be aging defects also, because as you keep using the IC, so these are all classified as defects. Okay, now these defects will result in it is very difficult to start working on defects. Like once you fabricated IC, if you want to find out is there any defect in the IC, it is almost impossible task. Okay, now so what we can do is these defects will result in some faults. Okay, the faults can be like some wire is stuck to 0 or some wire is stuck to 1. Okay, so these are known as faults. So detecting a fault is easy. Okay, and to give some test vectors and find out if there is a fault in the circuit. Okay, that is pretty easy. So a defect results into fault. So we generally look whether the circuit has gotten a fault or not. Okay, and then error is an so a defect will cause an error in the output signal. Okay, suppose an output is supposed to be for an AND gate, when if A is equal to 1, B is equal to 1, output is supposed to be 1, but you get a 0, right? So that means there is an error in the circuit. Okay, so what is our aim in this particular course? Okay, we will first model all the faults. Okay, and then try to give some input signals, and we have to observe the output for any errors. How this entire process can be optimized. Okay, so we'll learn about few algorithms, right? How to generate the test vectors, and what is the fastest way to detect the errors, right? So those are the kind of things which we are going to learn in this course. Also, finally, if there are many errors, then the computer itself can crash, right? So at the very functional level itself, because of these multiple errors, there can be deviation from the expected behavior. So this is how a defect can cause a fault, fault can cause an error, error can cause an failure. Okay, so this is some fabrication faults which the picture have been taken from your textbook. You see here, this is supposed to be a single wire out here, but there is a broken. So I hope it is visible to you all, right? Otherwise, when I share the PDF, it would be visible. So there is a breakage out here. Okay, so this results in an open connection, whereas it is supposed to be closed. Similarly, here this wire is supposed to end here, this wire is supposed to end here, but because of the fabrication, a small deposit of metal is there between these two wires also, and hence these two wires have become a short. So this is known. So both these things can happen during fabrication. Right now, the fabrications can be classified as random defects. Okay, so suppose two wires are running like this, and finally it has got fabricated like this. Okay, and there is no correlation across wafers and dies. Okay, so in a wafer there are 1,000 dies. It is there in 1 or 2 dies. Okay, then you can consider that it is because of some fabrication process. So a small percentage of that is happening. So you don't have, you just can't help it. Okay, because as we are moving down the technology, right, with devices shrinking, these kind of things can happen. So testing has to find out if such errors have such defects have occurred or not, so that we should be able to detect through our testing. Okay, but there could be some systematic defects also. Suppose across many dies, right, you are observing this kind of fault which has happened. Okay, then what, then there could be two things. Okay, one, your DRC may not be good enough, right? Right, so whatever spaces which you have given, they may not be enough. Okay, so if it is being observed in many dies and wafers, then obviously generally what happens is, if your DRC rules which has been set by the fab lab, if you have not followed that, then that will be picked up during your DRC check. Okay, after layout you do the DRC check and it will say, okay, these are all minimum spacing. Okay, but then if such occurrences are there, a lot of occurrences are there of this fault, then the fab lab will review the DRC. Okay, then either they relook at the DRC, or their own lithography and masking process, something has gone wrong there. Okay, so that needs to be, so if there is a systematic defect, then they need to find a solution for that. Okay, random defects is okay. So you can expect there will be a few parts per million defects like this. Okay, so that cannot be avoided. Right now, why is that we have to model? Why are we going to learn this modeling of faults? Okay, first of all, defects are hard to handle. Okay, there could be multiple defects in a circuit, and it is just impossible to start looking at from the defect point of view, right? But faults are going to be limited, right? So that is why, and it can be easily calculated. Right, calculated means you can give a set of inputs and monitor the outputs for errors. So this is pretty easy, and that is why. And a fault makes automation possible. Okay, so we can generate an automatic test pattern generation. Okay, first we learn about the fault models, then it will help us to generate automatic test pattern generation. So okay, fault simulation is okay. Is possible. That means you have made a circuit, and suppose you have made a circuit, you have written a Verilog code. Now you want to simulate some fault. Say at a point you want to see if this particular node gets to ground, what would be the effect of the circuit. Can you do that simulation? You just have to write a code accordingly, right? At that particular node, it is stuck at 0 or stuck at 1. So you can simulate that fault easily, right? And then after doing that, you can probably give an input signal and try to see whether the output is how to detect that, right? You can check with an let me explain to you. Suppose there is some circuit like this, right? Right now, I want to simulate an this is a wire here. So when I write a Verilog code, I can assign W is equal to 0, right? I can give that fault, I can simulate that fault, and then for how to find this fault. So what is the kind of input vectors you give, and which will give me a faulty output. All the vectors may not detect this particular fault, right? Only some particular pattern of input vector only will detect that fault, right? So that way fault simulation Okay, but if it is a defect kind of thing, right, everything is abstract. You can't how do you model it, or how do you do the simulation? So those, but faults can easily be done. Okay, evaluate a test quality. Test quality means once you have multiple faults, can your test vector detect all the faults or not, or are there some faults which are not detectable? So all those kind of things are possible. Okay, when we are speaking about faults and not about defects. Automatic diagnosis, okay, that is same as ATPG. And the faults, once the faults are identified, then the fab lab, right, what as a design engineer, what would you do? You would give some test patterns post fabrication, check the results, and tell the fab lab, see, okay, across many dies or in this particular die, these are the faults. Okay, stuck at 0 faults, stuck at 1 faults, and he can subsequently analyze that what kind of an defect it is, right? So he can do probably a thermal imaging. He can give some VDD and give thermal imaging and see what is happening in the IC. So it will give a fair idea about if there is an open or a close. Okay, so that will from the fault to defect will be done by the fab lab and fabrication guys. So as a test engineer, we will just try to tell, okay, these are the nodes at which we have observed stuck at faults, or right, those kind of faults. Now there are several kinds of fault models which is mentioned in your textbook. So one is known as assertion fault, in which you say, okay, this particular L line takes a value V. So these kind of fault models can be done, right? Or you could have behavioral faults, right, where you can electronic system, like you can say this wire, instead of an A and B, it is A or B. So that kind of fault you can write, but we are interested only in this, right? There are several kind of faults. Just for your theoretical knowledge, you could go through this. But what we are interested will be in structural faults, because all the ATPGs are based on structural faults. Okay, so the structure of a circuit may refer to so we like stuck at faults. If it is stuck at 0, there could be a bridging fault. Okay, so we'll study these in details in today. So these kind of, there are n number of fault models, which you just for theoretical purpose you could just go through it once, but these are the faults which we will be focusing in our course. Okay, now when we say testing, right, testing is not giving a certain input and trying to find the functionality, whether right, I am not in testing, I am not doing A plus B and finding if the result is A plus B at the output. Okay, what in testing I am doing is, I am giving some test vector, right, and at the output it is supposed to be 1, right, whether I am checking whether it is 1 or it is 0. If it is 1, I say it is okay. If it is 0, I will say right, then there is a fault in the circuit. So I am not really checking the functionality. Okay, only I am giving a particular a test vector. Okay, so each test vector will check some fault or other, right? So faults could be many. There could be multiple faults at different places, right? So one particular test vector may not be able to tell. Okay, so the number of may not cover all the fault sites. So you will require a multiple number of test vectors. So what we are going to learn in this course is, what is the ideal number of minimum number of test vectors are required. Okay, how to go about generating those test vectors and things like that. Okay, so now let's take this we said functional testing versus structural testing. What is the advantage? Okay, now suppose I have an 64 bit adder. Okay, 64 bits plus 64 bit. Now the total number of test vectors is 2 to the power of 129. Correct? Those many input combinations can be there, right? So 64 should be 128, right? Why is it 129? Anybody?
Previous carry.
Yeah, so there is one carry also. So there actually one more bit is there. So total 6.8 into 10 to the power of 38 different combinations are there, right? So if I have to functionally check whether this is going to work or not, right? So if I use 1 gigahertz clock, then it will take 22 years to complete the testing. Okay. So whereas suppose I am doing an structural testing. Okay. So this is a full adder, right? So I am not worried about, right, in the structural testing, because during formal verification and logic simulation, I have already verified in the software that if this gate is made like this, it would work as a full adder. Okay. In structural testing, what I am doing is I am just checking in fabrication if there is some error or not. Okay, so whether this is stuck at 0 or this is stuck at 1, this is stuck at 0 or this is stuck at 1, this is stuck at 0, stuck at 1. So there are 1, 2, 3, 4, 5 nodes. Okay, so in these five fault sites we say. Okay, these are the 5 places where faults can occur, and in these 5 whether it is stuck at fault. Okay, so these stuck at faults actually, even if the gate is made faulty, so it would come up as an stuck at fault. So so we'll see there are 5 fault locations. Okay, this is for the sum, and this is carry. So 1, 2, 3, if you see here, total 17 fault sites are there. Okay, these are known as fault sites. Okay, so there are 17 fault sites. So 17 plus 10, 27, right? So that is for one full adder. Okay, so how many full adders will be there? Such for a 64 bit, there will be 24. 64 bit, right? 64 full adders will be there. So there are how many total faults are there? It is 10 plus 17 into 64, right? So this is the worst case scenario, right? But many a times, right, if I give one test vector and I am getting a faulty output, that could have covered many faults in one go, right? So not necessarily. So this is the worst case scenario where one test vector is detecting only one fault, but that will not be the case. More often than not, in a single test vector will as we move forward, we'll see that single test vector will cover multiple faults. Okay, so I am not interested in whether it is if I give 111 here, okay, in the first run itself, right, in the first run I have found some fault here, right? So I am not interested in whether it is here or here. Say this particular test vector is detecting this or this, right? As far as testing is concerned, I am getting a faulty output, right? So it is okay for me. So that this I will just discard this gate or this particular circuit, right? So even if it is detecting 2 faults, it is not really making my test less reliable or something. In fact, it is better. That much lesser time I am taking for testing. So if a particular test vector is covering many faults, that is a good thing for me, right? So there is not an issue. So that is why we do structural testing rather than a functional testing. Is this thing clear to all of you? Yeah, Mrityunjay, Tabriz, what is the advantage of going for structural testing rather than doing a pure functional testing? Is it okay with all of you till here? Okay. Right. Okay. Now there are a few common structural faults. One is known as single stuck at fault, and there could be multiple stucket faults also. There could be transistors open and short faults, bridging faults, okay, and there could be delay faults and analog faults. Okay, analog fault is we will not discuss much about this because our focus is on digital. It is nothing but suppose I am supposed to get a 1.8 volt. I am getting only 1.7 volt at the output. Okay, so that kind of faults. So we'll talk about the first and four kind of faults here. See, this is now suppose this is an stuck at 0. Suppose I want to find out if this circuit is there, if there is an stuck at 0 at this point or not. How do I do that? So what is the test vector? First of all, if it is stuck at 0, I should force here a 1 or 0. Anybody? I want to check
1.
Yeah, I have to force a 1. Right? So I give 1 1 here. Right? Now for an OR gate, what should be the input here? For this now, so this particular
0.
Right? This has to be 0, because if I give 1 here, okay, it will get output as 1 here. Right? So I have to give a 0 here. So this test vector. So this is how for this particular stuck at 0 fault, the test vector will be 0 1 1 1. Right? So what we are going to learn is, first of all, for there are a few things which is from this a simple example, we know for a testing a few things are required. Okay. First is, okay, the fault, for a fault to be activated. Activated means if it is 0, I have to put a 1 here. Okay, that is the first step. Second, a fault to be propagated to the primary output. It is known as propagation to primary output, because finally we are going to in this test, as of now we are discussing the theory, finally we are going to do it post fabrication, right? So I cannot observe signal here. Okay, I can observe only signal at the output. So this fault needs to be propagated to the output. That is the second. And the third one will be known as justification. Okay, what is justification? For this fault, we have propagated, and from there we come back and assign the test vectors. Like this is for a OR gate. For the fault to propagated, the other input should be 0. Right? Now the fault has come here, but for this to be 0, I have to work backwards towards the test vector. Right? So that is known as justification process. Okay, so you need to activate the fault, then you have to do the propagate it, and then you need to do the justification. So these are the three things which we need to do. Okay, now this notation which we are going to use everywhere. Okay, so what is this notation? One stroke 0 means if it is fault free, it is 1, and if it is fault, it is 0. Okay, 1 means fault free, 0 means it is a faulty response. So this is what we are going to monitor at the output, and this notation we are going to use throughout in this course. Okay, it could be 0 1 also. Right? Suppose this test vector is here. If I have to write some, if I have to find out some fault here, I can write it 0 1. That means because I am giving 0 1, so it is specific to input vector. Okay, so this is not permanent. Each of these is specific to a set of input vector. In this particular case, 0 is right, is the normal thing which is to happen, fault free, and 1, if there is a 1, it is faulty here. So this is the kind of notations which we are going to use. Right? Okay. Here, how many faults are there in this circuit? How many fault sites? Anybody? Total
Only
number.
one, three.
Yeah, 3.
Three.
How many faults? How many faults?
Two.
Like
Two.
there are 6 faults,
Six.
right?
Six spots. Yeah.
Stuck at 0, stuck at 1. Okay. What is the minimum test number of test vectors? Just to guess. You'll have 4 different combinations, right? Yeah. So all the 4 will be
Yes.
required. Okay, let's see. It's too early to ask you that question. Okay, so let's see how to. So total with only 3 vectors, we can find out all the 6. All the 4 is not required. Okay, let's see. Like suppose input is 0 0, output is fault free. Okay, and then this table says if A is stuck at 0, what will be the output? Okay, output will be 0. A is stuck at 1. Okay, what would be the output? Because B is 0, it will be 0. If B is 0, then output is 0. B is 1 if it is stuck at 0. If C is stuck at 0, it will be 0. But if C is stuck at 1, okay, if the output is stuck at 1, it will be 1, right? So this test vector is required, okay, to detect this fault. Okay, C is stuck at 1. Now suppose I give this test vector 0 1, and then fault free operation, it will be 0, right? If A is stuck at 0, I'll get 0. A is stuck at 1. Now A is stuck at 1, I am giving an input vector 0, right, but it is 1, and right, it is so I'll get an output as 1, right? So what does red indicate? That it is different from the fault free operation, right? So this is 1 out here. So 0 1, if I give fault free will give 0, but a faulty A1, I'll get 1, right? Even if C is 1 also, I'll get 1 here. Okay, so similarly if I give 1 1, fault free will be 1, and A is stuck at 0, then I will get an output as 0, right? So that means A stuck at 0 can be detected by 1 1, right? And like similarly B is stuck at 0 can also be detected by this vector. C stuck at 0 is also can be detected by this vector. So have you understood what this table stands for? These are the input vectors. So these are the output vectors, right? And these are the outputs with these faults, right? So if you see here, so from this table, how many test vectors are required? What is the test vector which is redundant?
One.
Yeah, the first one, right?
0 0.
Yeah, this test vector C stuck at 1 is actually with this test vector also I can find right that whether it is C stuck at 1, right? Here this test vector is required because it is a single one here, right? And similarly this is single, so this test vector is also required, and here also single, so this also is required. So 3 test vectors. So this is all about, this is manually for a small circuit I can I can see, right? But what we are going to learn in this course is for big complex circuits, there has to be some algorithm, right? And finally, what I need, what I need finally is, okay, set of test vectors. This is the set of test vectors, right? And then I have to tell this is the fault free operation. These two data will be required to be given to the testing chap, right? And before I start making this, right, I should have a total number of faults which are there, which is possible in the circuit. Okay, so this data, so I should be able to cover all of them. So this is what is testing is all about. Okay, right now this is an XOR gate, okay, made. So you can see
Excuse
the,
me, sir.
yeah, tell me.
Sir, on the previous slides, I have a question. For the third scenario, that is 1 1, we have like 3 different faults that can be found, right? So,
Yes.
once we test 1 1, how do we know where the exact fault is? Like, how do we localize the fault?
No, we need not
Uh,
localize that. That's what. right?
Okay, so we just need to find out if there's.
We will just say that this circuit, okay, we will say, okay, this circuit is faulty because one of these faults is there. We tell the fab lab.
Okay,
Okay, it is up to him to find out, right? Because if you try to do each fault, then that will unnecessarily waste testing time. Okay.
okay,
From the user point of view, I am not interested. My point, from the testing point of view, I have to do 100% coverage of all the faults with minimum number of test vectors.
okay,
Right? That is my goal. Now, each test vector, that data also will be available. Okay, during this particular test vector, the test has failed, and one of these faults could be there in the circuit. So that data I will give it to the fab lab for them to analyze. Okay, it is now up to them to find what could have gone wrong. Okay, we will not spend time on that. Okay. Okay.
thank you, sir.
Okay. No problem. So this is like another XOR gate where these are all known as now if you see here, this is A. Whenever there is when we do the fault modeling, okay, single stuck at fault modeling, right? So we say that whenever there is a connection taken, whenever there is a branching there in the wire, we take these three as three different nodes. Okay, that means C can get stuck at 0, whereas a D need not be stuck at 0, right? So we take into consideration those kind of things also, because there could be problem with the contacts and things like that, right? And there could be issues. So when we do whereas these wires, okay, they are direct connections. Here we don't expect that this output and this input will be different. Okay, so wherever there is a branching, okay, we consider that as three different nets. Okay, we just consider them as different nets. Okay, whether it is 3 or 4, that depends on the number of branching, right? Here there are 2 branches, so total number of 3 different, we take it as 3 different. Now if there is one more wire coming out here, then obviously that will be another net. Okay, so in our model which we are going to learn, each of these nets, wherever there is such branching, they will be taken as a different net. Okay, and accordingly for each net there will be a stuck at 0 and stuck at 1 fault. Okay, so that is about singles. Now this is why I am telling single stuck at fault. We are assuming the fabrication process is reasonably okay, and for a small circuit there will be only one fault. Okay, we are not talking about 2 faults happening together. Okay, so we are assuming that only one fault is there, okay, in the circuit at any given time. So that is why we call it as single. But that single fault can happen anywhere. Okay, there is a difference, right? I am not saying that. I am telling at any given time in a particular circuit there will be one fault. Okay, but that fault can happen anywhere. So I am taking all possibilities of faults in that particular circuit, but only at any given time only one fault. Okay, so that is the way it is. So in this particular circuit, okay, if you see here, now these nodes have been taken, E, L and F have been taken as different. Okay, now when I make the truth table, okay, for 0 0 0, this is the good output. Now I have an I'm just not talking about an A, H, K, B, C. Let just focus on this, right? So if this is a focus, so these three, so I am writing if E is stuck at 0, F is stuck at 0, L is stuck at 0, these three. Similarly, E is stuck at 1, F is stuck at 1, or L is stuck at 1. Now what would be the output? Okay, these are the outputs, right? So now if you see here, E is stuck at 1 and F is stuck at 1, L is stuck at 0, right? So they are different, they are not the same, the outputs are not the same, right? So you will find here, if you see here, right, they are not same. right? So now these are different faults, and these different faults will require different test vectors to identify these faults. Is it understood? Right? When I'm doing a branching operation like this, right, this fault is different from this here, this fault is different from this here, right? So F stuck at 1, right, is not same as E stuck at 1. Okay, so other way around also. So you will see from this table. So when their branching is happening like this, each fault needs to be considered as which is not dependent on each other, right? So you have to consider that as a different fault site, and accordingly you got to make a truth table and see whether what are the test vectors which are really required to identify those particular faults. Okay, now here there is did you observe something from this table? There is an issue here in this table. Anybody? Is there?
So when L is stuck at 1, then input 100 should not give the right output, right?
When L is stuck at 1, okay,
And A is 1, so H becomes 1.
uh,
Okay, it is an OR gate. Okay, sorry.
right?
Okay, will be
Okay. So what is the issue now?
So we cannot detect L is stuck at 1.
Right? We cannot detect L is stuck at 1. Okay, why so? Looking at this circuit, okay, let me explain why.
So because if I need to detect L is stuck at 1, I need to deposit 0. And if I deposit 0, then J becomes 1. And it overrides the output at K.
Correct, right? So there is no way I can find L is equal to 1. Okay, I'll tell you what is the reason. Okay, now this is 1, 1, 1. Okay, so can I write the expression like this? From here, I have made this truth table. Okay, from this circuit, I have made this truth table. There are 3 min terms. Okay, for output to be 1. So can I write this like this? Right? This is what? A dash, B dash, C. Right? This is A, B A dash, B, C. And this third one is A dash, B, C. Okay, I have written here. I take an A dash common. Right? So I get this. Okay, right? And this is just a simplification. I do this. Right? And from here I get this. Right? So if I simplify this, right, I get this. Okay, if you see here, what is A or B plus C? So B plus C is this E, right? And then there is an this J is nothing but this portion, and then there is a NOR here. Here it is actually A. That means this gate is not there, right? This is the same circuit, so there is no function of this gate. This particular K is actually like this, actually simplified version. Is it okay with all of you?
So one doubt. So in the table, so for L/1, shouldn't it be 1? I don't understand that part. How are we putting 0 there?
Where? Here?
Yeah.
If I give 0, 0, 0 input and L is stuck at 1, okay?
Okay.
Then what will happen? I will get a 0 here, but from here I will get a 1. 0, 0 will give me 1 here, right? No, 0, 0 will give 0 here. I will get a 1 here, then I will get a 0 here. So I cannot detect that fault. Okay. Is it okay, Rahul?
Okay.
Right?
Thank you.
Now, when I am analyzing this, okay, I am finding it, this gate is redundant actually. There is no purpose of this gate. I can give A directly here from this Boolean simplification. Okay, right? So now what can we say about testing? Does testing does something else also?
So just optimization.
Yes. See, when we are going to make some algorithm for finding out faults at all these locations, and on completion of algorithm, if I am finding that some fault is not being detected, then that means in my circuit, okay, there is some redundant portion. Okay, so testing also helps us to find out if there is some portion of the circuit which is redundant. Okay, so invariably if there some test is not being some fault is not being detected, then we can say there is something wrong with the circuit, there is some redundancy somewhere. Okay, so that is another aspect of the testing which we should remember. Okay, so whenever there is some redundancy, there is an issue. Now there could be multiple stuck-at faults also, right? That means more than one fault at a particular given time. So if there are n possible fault locations, okay, there could be 3n fault sites. No, 3n fault on that line, right? Because that line could be stuck at 0, or that line could be total. There could be 3n possibilities, because there are n number of line fault locations, and that each line can either be stuck at 0, stuck at 1, or it could be good also. When I say good, it can take a value of 0, 1 depending on the inputs. Okay, so there are 3 different possibilities, and there is one possibility of the entire circuit being good, right? And no, when I say there is a single stuck-at fault, right, then there are total n number of lines. So 2n possibilities are there for a single fault. So total number of multiple faults will become 3n minus no fault, okay, minus total number of single faults. Okay, so this. So in practice, multiple faults are not considered. Okay, now why it is not considered is like there was several studies have been done. So this is one paper which you could refer, in which what he did is they took an ALU, okay, 74181, which had 400 stuck-at faults, and they this is simulation based. Okay, so they had 79,600 double stuck-at faults. Okay, they were like two stuck-at fault conditions, and then they used different algorithms. Okay, so these are all different algorithms for testing, preferred by proposed by different people. So these guys, they carried out trying to find out with different algorithms a total number of test vectors which they applied using the first. When they applied 12 test vectors, total undetected double faults were only 9 out of these many, right? Because if you are trying to find a single stuck-at fault, obviously it will cover generally multiple stuck-at faults also. So from these results, one can say that okay, some algorithms, they use a shorter test, and not necessarily if you have large number of test vectors that you will have like here, right? 14 have been used, and you got 4, only 4 got not detected. In this particular algorithm, they have used 17 vectors, but 30 have not got detected double faults. Okay, but all the single faults have been covered. So they have algorithm 1. They required 12 test vectors to cover all single stuck-at faults. Okay, on completion of that algorithm, they found that 9 multiple has got left out. Okay, so like that. So if you see here, so if you finally from this we can say that okay, so generally, first of all, the probability of multiple stuck-at faults, given that the technology is reliable, is very minimal. And then when generally we are talking about trying to find out the single stuck-at faults, most probably the double stuck-at faults or multiple stuck faults will get covered as it is, and that is why we don't bother about multiple stuck-at faults, okay, in all our algorithms which we are going to learn, right? So now for example, okay, this is an stuck-at 0. Now what could be the test vector to find this fault? Can somebody say?
Sir, A0, B1, C1.
Let's go step by step, okay. First of all, this is A stuck at 0, so what should be the vector which I should give here for C? 1, right?
1, yeah.
Right? Okay. Now, if it is 1, for this to propagate here, okay, what should be here? 1, right? Because if I give a 0 here, right, then this will be 1. So I have to give 1 here, right? Only then this will get propagate here. So here I can write that. Can I write it like this here? If it is fault free, it will be 1. No, 1 1 should give 0, right? So if it is fault free, it is 0.
0/1.
I can write it as 0/1, right? Now I am coming here. Okay, now I want to propagate it here. So here it should be 1, right? So here I have 0 1. Then what will be here? 1/0.
Yes.
Right? Okay. Now I have propagated this. Now I come back here. Okay, I require a 1 here, right? This is already 1 here. So this has to be 0. Okay. So this is how we go about. So 0 1 1 is the test vector which will be required for this. Okay. So this is how the algorithm works. Now suppose there are 2 stuck-at faults, okay, then 0 1 1 is not possible, right, because this is stuck at 0, right, this is stuck at 1. So 1 1 will put a 0 here, right, and that 0 will make it a 1 here, right. So this fault is masking this fault, so I can't find, right. So this test vector is not good enough. So 0 1 0, okay, if I give 0 1 0 test vector, then both these faults will get right, and I will find, right. If I give 0 1 0, right, and 0 1 1, if I give 0 1 1, then I'll get an output of 1. So that is an kind of correct output. So I have to give 0 1 0, okay, and then both these faults will get detected. So this is what we are going to learn, how to this one we did it manually, right, but there has to be some algorithm. We cannot, if it is a big circuit, we cannot start taking a pen and paper and start doing like this. It is going to take time. So this is what we are going to learn in this course, how to go about setting these things. Okay, now there could be something known as bridging faults. Okay, bridging faults is initially we talked about stuck-at faults. Okay, the second kind of faults is bridging faults, where the output and the input are shorted like this, or two inputs are shorted, or the outputs are shorted. Okay, and these can happen because improper masking, right, or during the etching process, loose wires, okay, defective print PCBs, shorting of pins of etching. So these things can result in these kind of faults. Okay, now it says the test vectors for input to output stuck-at faults cover input to short outputs. That means this stuck at fault, right? This can be detected. Like for example, if I have to check A stuck at 0, right? What is the test vector I will give? I'll give 1 1, right? If I give 1 1, I have to get an output as 0. But if there is a connection like this, I will get as 1. So those test vectors which we are using for stuck at faults will detect these kind of faults also. So you don't have to actually go for additional testing for this particular, the first set of input to output shorts. Okay, so you don't require additional test vectors. Okay, so the same test vectors for stuck at faults at these nets will identify these faults also. So no additional testing is required. Now what about this and this, right? So but these can this kind of things can cause oscillations, right? And it can cause memory like oscillations, because this has become a latch. And we saw in our advanced VLSI class, right? What is a latch? Like suppose I am giving a signal A equal to 1, right? So, and this has for some reason it has become 1. No, suppose I am giving A is equal to 0. This has become 1, right? So that 1 can come here again, right? And then suppose this is 1, and that can become 0 here, right? Again that 0 can come here again, it can push it back to 1. So you see it can become as oscillations. Also there could be cases where this feedback can store data even if without an input, right? It becomes a memory kind of thing. So these kind of things can happen, right? Now when the output, right, there is a short, and that's the same for the input case also. So you could model it as a resistor between these two outputs. Okay, so these can result in an wired or wired and an F dominant. Okay, it could be G dominant also, but I'm just giving one example of F dominant. So there could be one more which is known as G dominant. Okay, now 0 0, right, and 0 1, and so for these things, if you see here, if for a wired OR, right, for I am giving 0 1 here, 0 1 here, right, for an wired OR bridging fault, okay, the output will be 0 0, right, and for an now this is the original outputs FG, right. So even if one of them is 1, both of them becomes 1, right? Even if one of them is 1, both of them will become 1, because there is some bridging fault here. That means the power supply line VDD is very strong. It is able to pull the 0. So the ground for this, suppose the ground here is weak, and VDD here is strong, right? In that case, it can become a wire. So that means it is not directly connected to VDD, right? It is coming through some PMOS, right? So if this PMOS is very can provide much higher current than the NMOS, which is sinking this current, correct? If the current which is coming here, right, from the PMOS is much more than the current which is being synced at this ground by this NMOS. From this NMOS is coming from this particular circuit. This PMOS is coming from this particular circuit. Okay, so it depends on which transistor is driving this to one and this. So if this is stronger, obviously it will result it as an wired OR, right? But if it is the other way around, if this this NMOS in this particular circuit is stronger and this PMOS is weaker, right, then it could result in a wired or this thing okay, wired AND connection. Okay, and there could be some situation where this is F is dominant. So both this NMOS and PMOS here is strong, right? And the NMOS and PMOS of this particular thing which is driving this node is weak. Okay, in that case, whatever is happening at F, that will be dominant. So that is known as a dominant. Okay, so you could get this kind of results at the output. Okay, G also could be dominant. Okay, so these are the things. Okay, so these are the all possible combinations which can happen because of an short between the output nodes. Okay, so but if there is a very weak link here, right, not a very strong ring, and then a very thin wire has got deposited, which has got high resistance, then that high resistance may cause a small amount of current, but they may not swing the logic, okay, from 0 to 1 or 1 to 0. Those kind of things cannot be detected, okay, through testing. Okay, they can be detected. Those kind of things can only be detected through, say, thermal imaging, right? When you do thermal imaging, you will find this portion is red hot, right? So that kind of thing can be done, or we can also do some power analysis of gates. Okay, when we do the power analysis, and if you find that this is actually making a path between VDD and ground, and then if you find that the power is much more than what is expected, then you can say, okay, this particular, somewhere in this particular circuit there is some bridging fault which is causing a short between VDD and ground. Okay, so for each module probably you can just do a simple power up and see whether there are some VDD to ground paths. Okay, so those kind of things can be done. Okay, so this is about how bridging faults is done. And now depending on what is the model, okay, the test vector will be different. Okay, like for example, if it is a wired OR out here, okay, if it is a wired OR out here, right? So wired OR, so this is the output, okay, which you will it will get 0 0 for these test vectors, whereas for fault free it is 1 1. Suppose this is wired AND, okay, the model which you have taken, okay, for those also it is the same test vectors, but if it is A is dominant, okay, then only this test vector will identify the problem. So this test vector, if A is dominant, it won't identify the fault. Okay, because expected output is 1 and this is also fault is 1, but A is dominant, that fault is there, right? In spite of that, this particular test vector cannot identify A dominant fault here, right? So what I want to say is, for different the way we have modeled this particular bridging fault, right? So accordingly the test vectors requirement will be different. Okay, so we need to choose the correct bridging faults. But then as we move forward, again some study was done here, right? And then they did with various algorithms, and they did with just single stuck at faults. Okay, again they were this is one of the standard ICs which they took for simulations. Okay, and then they saw when they were doing single stuck at faults, right, 98% of the bridging faults also were, so they induced some bridging faults also, and then they I think here it is somewhere written, it's not there, if it's not written you could refer to this, they induced some amount of bridging faults also. So and then they saw that just by doing single stuck faults, okay, 98 to 99% of 97, you can say 97 to 100% of the faults were being covered. Okay, so that means even if you do single stuck faults, okay, so it is good enough. Okay, so what we have come now, we said we talked about single stuck faults, then we talked about multiple stuck faults, and then we talked about bridging faults. Okay, but then we also realized that it is not worthwhile, because if you start trying to make algorithms to detect multiple stuck faults and bridging faults, we saw there's a lot of complications involved, right? because if these are on the way it is being modeled and all, so that will increase my testing time. Okay, so it is going to complicate things and make testing more difficult. But then it is not no, worthwhile spending that much time, because several studies have shown that multiple faults as well as bridging faults are more or less covered by the. So this is an good indication that this is a good fault coverage. Okay, anything above 95, 96 is considered as a good fault coverage. You don't have to target 100%, and that is why henceforth we will not be focusing too much on these two kinds of faults. Okay. Now another kind of fault which could happen is a delay fault. Okay, suppose this is an OR gate. Initially I have 0 0, and one of the inputs is making a transition from 0 to 1, right? And if it is fabricated properly, then this green line, okay, which is that means it is making a transition from 0 to 1 within the stipulated time. Okay, but if it is making an delayed rise, okay, so you find here the propagation delay is large because of some fabrication issues, then it is an fail. Okay, the test is fail. Okay, so now these kind of things are known as delay faults, and as you can see here, right, that two sets of test vectors are required. Okay, you give because it is a transient condition, we are seeing rise time or fall time, so you need to give one set of test vectors followed by the second set of test vectors. Okay, so you will require two. So you can say the kind of faults you can model as slow to rise and slow to fall. So STR and STF. Okay, and why does this thing happen? Because if there is a VT variation during fabrication, right, and so because when the oxide is being fabricated, the thickness of this oxide or some impurities in the oxide can make the can cause a small VT variation, and VT variation can if the VT is higher, then it can result in lesser currents, and eventually that will result in slower rise time and fall time. Okay, or there could be some improper contacts, okay, which could result in higher resistance, right? Or if you have used very thick wires and not taken care of, and if you have something running parallelly below that and all, it could result in higher capacitance. Okay, normally the upper and the below layer of the metal should be orthogonal. Okay, but in some cases, if you have not taken care of that, and if you have some abnormal capacitances associated with that line, then a large capacitance can again result in higher delays. Okay, so these are the things which can come during fabrication, right? So they can be modeled as a resistance and a capacitance. Okay, so this RC model. You could have an R here, C here, either way. So these kind of things can happen. I think I have this. This should be here. In fact, there is an error out here. Right now, if you see here, what happens in an actual operation. So suppose this is a circuit in which A is making a transition from 1 to 0, and B is making a transition from 0 to 1, and if these gate delays are in normal, then this is making a 0 to 1, this is making 1 to 0. Okay, so this input is like at any given time, one of them is 0, so output continues to remain 1, no issues with this. But if during fabrication a stray capacitance has come here, okay, or some large resistance has got fabricated here, right? Okay, here okay, this is correct. Okay, what it means is during fabrication, suppose a resistance has come in here, right, during fabrication, because of this wire you have used a very thin wire, or because of the higher VT here. Okay, so that can be modeled as a higher resistance here, and similarly a capacitance because of the improper wiring which we have done, if some stray capacitance is there, so this can happen, right? Okay, now coming here, suppose there is a capacitance out here, so this is making a 0 to 1, okay, early, but this is not going 1 to 0, it has got higher propagation delay. Suppose this gate as with respect to this inverter, generally we try and size these transistors. We saw in the last course VLSI design that we try and make all gates delay equivalent to that of a unit inverter. Okay, so but suppose because of this, although theoretically we have designed this to be that of equal delay equal to that of a unit inverter, but because of fabrication of this extra capacitance which has come here, so this is it has got a higher fall time. So this is, if it is going late, then you will have a situation where this is 1, this is 1, right, and then and hence the output can go to 0. So you could have a glitch at the output. Okay, so these can adversely affect your functioning of the entire circuit. Okay, so this is what and path delay fault is all about. Okay, so we have to ensure that such faults does not exist in the circuit. Okay, now for example, how many paths are here from the input to output? Anybody?
9 paths. 9 paths.
This is one path. Okay, this is the second path, right, and this is the third path, and this is the fourth path, correct? Do we have more paths? It says 5 paths.
Oh, it's 5 paths, yeah.
Yeah, this C also can go like this, right? So we need to detect, okay, delays in these paths. Okay, so there are how many set of test vectors? Okay, for all these paths, right? So each of these paths I have to give 2 test vectors, right? One test vector first and then the second test vector to put it to. In fact, this is only for rising. So if I have to find out falling also, then I will have to give another set of test vectors. Okay, so that is there. Okay, now okay, let me. Now suppose I have to find slow to fall at F. Okay, here. Okay, slow to fall fault. So I give a test vector first 0 0 1. So this is going to be 1, right, and then I put a 0 here. So this edge will fall. If this edge will go high, right, so I have to put a 0 here in that case. Okay, for this OR gate. So this 0, so and hence a becomes 0. So in the next, so this is the test vector. So this particular test vector, okay, 0 0 1, okay, followed by 0 0 0 will tell me about this path. Is it okay? Understood, right? So this is how. So in general, when we say an AND gate, okay, if we have to propagate something, a fault like this, generally for an AND gate we will give 1, right, and for an OR gate, if we need to propagate something, we will give it as a 0 out here. Okay, these things we will see in detail in the next class. Okay, when we learn about propagation of these faults and all, but you can just remember this, right? Because if a AND gate, if I give a 0 here, this output will get masked. Okay, similarly, if I give 1 here, the output will get masked. Okay, then this is not reflected here. So that is why for an AND gate we give 1 and for an OR gate we give 0. Okay, so these are the 2 test vectors which are used. Now this is there is something known as non-robust test and for robust test. Now for finding out, okay, whether here right? A fault, what does STR stands for? If you go back, no, slow to rise. Okay, so if I have to find a slow to rise and a fault at here, I have to make a transition 0 to F here, right? So if I give this test vector, this followed by this test vector, right? Then here also it will make a transition, right? Here also it will make a transition, right? So I cannot be very sure that this what I am observing here is because of this or because of this, right? So this is a non-robust, so this is not a very good test vector. Okay, just giving this A as 1 and C as 1 and switching from B0 to 1 will cause this rising at both these places. So this is not a very good test vector. It is a non-robust testing. For a robust testing, I can give this A equal to 1, B equal to 0, and C given switching, I switch C from 1 to 0. In this case, if you see here, only transition is happening at this E node. So this is testing of E. Okay, so this is known as robust testing, right? Robust testing. So we have to identify that test vector which is robust for a particular node, right? This can give us wrong results also. Okay, so that is what is important. Right, robust testing may not be possible always. Okay, now if you see here this particular circuit, okay, this is the K map, right? So did I discuss this particular circuit about hazards in our VLSI design class? Anybody? No, right? Okay, doesn't matter. So suppose I make this if I have to implement, okay, this particular function, okay, if I implement, just take these two and these two, right? AB plus BC, okay, only this much portion of the circuit with a 2 input OR gate. Is it the same function? This and this, will it be the same function? You learnt about K maps, right? Right, when we do K maps, this one can be clubbed like this, right, which is shown as red. This also can be clubbed like this, right? So
Yes.
so
Yes.
if I do just this much also, this function can be realized, right? Isn't it?
Yes.
Right?
Yes.
Okay. Now the problem with implementing only this much is, okay, now suppose B is making a transition from 1 to 0, right? So there could be at the output, right, and 1 is supposed to remain 1, but if you see here in this path there is only one gate. Here there are 2 gates, right? So propagation delay is more, so there is a possibility that it will go to 0 and come back here. Okay, this is known as hazard. Okay, I will talk about I'll show some waveforms in the advanced VLSI design course exactly for this particular circuit, but just understand, if I do like this, there is a possibility of hazard. Okay, so where does this hazard actually come from? When we make the K map simplification, okay, when we use the tools or we do it manually, we are clubbing this 1 and we are clubbing this 1 and this 1 we are leaving it. Okay, so whenever we leave 2 adjacent ones, okay, although they are covered, okay, so the basic requirement is taken care of by clubbing this and clubbing this. Okay, so functionally there won't be any problem, but during transient conditions, if these 2 ones are left alone, then they could cause some this is known as hazard. Okay, now to avoid that kind of hazard, you need to club this also, right? So you make an additional gate here. So if you make this additional gate out here, right, so this is actually a redundant gate. Okay, and if it is a redundant gate, then Okay, the thing is, such hazard can be avoided. Okay, so a detailed analysis of this I will do it in the other course. But just understand here. So this is so that it is when we make such redundant gates, okay, some testing of, like we said, some testing of stuck at fault at here cannot be done. Okay, in this case, and also we don't get an robust this thing. Test pattern will also may not be available. Okay, although this is not a desirable thing, okay, for testing, but functionally it might be important. Okay, so because this kind of hazard, right, this can go and create a panic in the next stages. Okay, so this actually it is supposed to be 1-1, but because of this small negative spike, it is possible that that 0 is being captured in the next stage. Okay, there could be a lot of issues. Okay, this can cause lot of unnecessary power consumption and all. Right, so from the circuit designer will feel it worthwhile including these kind of redundant gates in many circuits. Okay, but these kind of redundant circuits is a nightmare for the test engineer, right? Because once you insert these redundant circuits, those the test vectors and those faults may not be detected at all, and when we run the algorithm, since that test vector is not coming up, right, the algorithm will keep running, generating many test vectors randomly, trying to fix that. So we'll see when we learn about the algorithms, right? So it will the algorithm will take lot of time, because it will unnecessarily, it won't know it is redundant, right? Finally, when it is not able to find this fault, it will say, okay, this fault is not there, but in the process it will consume lot of time. Right. So when we make the when we initially make the fault matrix, right? Fault matrix, that is the total. When we list down all the faults, so the test engineer or in the design engineer, the circuit design engineer has to tell the test engineer, okay, there is some redundancy in the circuit. Please don't waste your time trying to, because he wouldn't know. A test engineer may not know, okay, this is a redundant circuit. He will, right? So that whenever an redundant portion is being incorporated by the circuit designer, he needs to tell the test engineer, okay, bhai sahab, dekho, I have got some right, redundant portions in the circuit. Please take care of that. Don't include that in your fault list. Otherwise, you will land up wasting time in trying to diagnose that fault, because those faults are not detected, not detectable at all. Okay, so that kind of thing is required. So that kind of communication is required between the circuit designer and the test engineer. Right. This is another thing. Like this is the stuck at fault. Okay, and this is the delay fault. This is for some, again, taken from this web page, and this is the bridging fault. So if you do 100% stuck at fault, okay, only 12 plus 3, 15% of the bridge fault will go undetected. Correct. Similarly, if you do the stuck at fault, only 32% of the delay faults will get undetected. Okay, so generally we do a stuck at fault, and we don't bother much about the delay and the bridge faults. Okay, so our focus will be at stuck at fault. And also when we are going to learn about this static timing analysis in our advanced VLSI course, we will see that we generally we go for process variations, OCV variations, where we cater for some slacks. Okay, slacks are nothing but we like, suppose there is a setup requirement of 10 nanoseconds for each flip flop. Okay, we will assume, okay, we will cater for 10% variation which will come during fabrication, during voltage variations, temperature variations and all, and we might want to keep the setup actually 10 suppose 10 nanosecond is the minimum hold time requirement for a flip flop. I might want to keep it as 12 nanosecond, right? So that even if it is while getting fabricated, if there is some delay faults, still that is delay the setup constraint is not violated. Okay, so when we do static analysis, we will see that. Okay, so this portion is really taken care of during our STA analysis. So there is an all the tools also like prime and things like that. We can set that percentage. Okay, so if you are not very confident about your fabrication process, right? So that is given as a variable to you, right? So if you are very confident, say you are fabricating at an 180 nanometer technology, which is very robust technology as of now, then you might want to give only 5%. You might want to cater 5% for your OCV variations for your timing analysis, right? But suppose you are making a circuit for 7 nanometer, you might want to cater 20% in your static timing analysis. Okay, so so that during fabrication, if there is some extra delays or something like that introduced, that can be taken care of. Okay, so henceforth again, like why I want to, we have discussed all these things, but our focus will be at on this stuck faults. Okay. So these are some of the suppose for example I have a 0 input as 0. There are two inputs. Okay, this is the mux. Two inputs are given here. The control here is also 0, right? And the output is also 0. Okay. Suppose this is the three inputs and this is output. If I am getting a 0, okay, then what are the faults which get covered? Okay, let me just. So when if I get 0, 0 and 1, and if the output is still 0, right, that means it is the correct output, right? I am giving a 0 here and I am giving a control signal 0 here and input is 0 here. Okay, input 1 here it is 1, but this 0 is being routed here correctly, right? That means I can rule out that it is stuck at 1. Okay, it is not stuck at 1. So this fault is already covered. Similarly, this output is not stuck at 1. I can rule out that also. Similarly, I can say this control input out here. Okay, this is also not stuck at 1 because I am giving 0 and this is being routed here. So by giving 0, 1, 0, okay, I am ruling out 3 faults in one go. Is this okay? Is the top one okay? All of you? By giving this test vector, if I am getting a 0 here, then I am ruling out, okay, 3 faults I have already covered. Now I change the test vector as 1, 0, 0, right? And if I am getting a output as 1, that means this is not stuck at 0 now. Okay, obviously 1 is coming here, that means this is not stuck at 1, and the output is also not stuck at 0. Okay, now this is also now over, right? There are total how many inputs? 1, 2, and 3 inputs, right? So now the third test condition which I am giving is 1 and 0 and control 1, right? So from 1 I am giving a 1 out here, and if I am no, I am giving a 0 here and giving a control signal 1. Now this 0 is being propagated out here. So that means this is not stuck at 1. So this is not stuck at 1. And the control is also not stuck at 0 because the control is 1 now, and because it is 1, this signal is coming here. So this is also taken care of, right? And then finally I give a 1, 1, 1 here, and I am getting a 1 here. So this will say that input is not stuck at 0. So now if you see here, there are 3 inputs. Now 1, 2, 3, 4, right? With 4 inputs, I am able to cover all the stacked faults. Now if I try to make a module out of this, there are 2 inputs, 3 here, 4th output. Okay, so totally how many fault sites are here? for this mux?
4 sides.
Four sides. So how many stuck-at faults? There will be 8, right?
Yes.
8. But here also I think one is redundant, right? This stuck of 0 is already covered here. So only 3 test vectors are required. Correct? Only 3 test vectors are required here. Right? So this is how this optimization needs to be done. This is all we are discussing in manual things, but we will see how the algorithms work as we move forward in this.
All 4 are required.
Why this stuck at 0? All 4 are required.
That is input 1. That is input 1. IN1.
IN1.
Earlier we covered IN0.
Okay, all 4 are required. So let me 1, 2, 3, 4, 5, 6, 7, 8. Yeah, yes. Let me do it now itself. Otherwise, I'll upload it as it is.
So that line is
No, I
correct.
think that statement is correct, sir.
Which one?
The statement is correct. Like only 4 vectors for 3 inputs.
Oh, okay. Oh, sorry. Yeah. So I made all these things. This my first course. So there could be some errors in the slides. You could let me know. Okay. Now there are some other faults also, which is known as transistor faults. Okay. The transistors can be stuck in open position also. Right. Stuck in open position means right. Even if you give a gate voltage, it will continue to remain off. Okay. And there could be stuck short fault also. That means even if you are not giving a VDD, then the transistor is on. Okay. So this particular fault can be detected by high IDD. Okay. This will result in a path from VDD to ground. Okay. So this is like stuck at this is open, permanently open, this one. Now how to detect that like if you see here, this cannot be detected by a single set of vector. Okay. So fault free, it is an NOR gate, right? But suppose initially I give a test vector of I have to charge it to 1, so I give 0 0. So this is charged to 1, right, from here, right? And then I give A equal to 1, right? This is supposed to go to 0, but it won't go to 0, right? So these kind of faults cannot be detected by a single test vector. I will require 2 test vectors. So initially I give 0 0, then I give 1 0, and if it continues to remain 1, then I say okay. So there is a fault here. So all stuck open faults also requires 2 vectors. Okay. Now for this particular vector, I require 2 vectors. Right. So these are known as transistor faults. For all transistor open faults, right? You require 2 test vectors. So that is again because of the fabrication issues which would come. Right. So now this is like this is one. You can verify this in your own spare time, right? So this is the stuck at fault. Like this is the initial vector, test vector 1, test vector 2. So as you move from this vector to this vector, okay, this fault F1 can be detected. Now F2, okay, this stuck at open of this transistor can be detected by this test vector followed by this test vector. Now F3 and F4, these faults can be F3 is here and F4 is probably here. Okay. So where is F4? Can you see F4 somewhere?
Near the ground terminal.
Here. Yeah. Okay, this transistor, no, if it is stuck. So so this can be detected, okay, by one of these. You can take one of these test vectors and move it to this test vector. Okay, so these are 2 sets of test vectors will be required to detect all these faults. Okay, So automation available for optimizing all these faults are there. So these kind of things can be done. So 2 pattern tests are required for test open faults. Okay, whereas for stuck on faults, okay, test pattern is not won't detect it. What will we don't monitor the output, but you will find that if you give 1 0, right, this transistor is supposed to be off, but if it is stuck at 1, you have a path from VDD to ground. Okay, so whenever there is a stuck on fault in CMOS technology, invariably, okay, there will be some path which will be available from VDD to ground. Okay, if that is available, then for when we power up the circuit and give some test vectors, if you find that there is for some test pattern, okay, if there is some abnormal current being drawn from the VDD, then you can say that it is an stuck on fault. Okay, so that is the way we can find. Now we said that stuck open fault, you require 2 test vectors, correct? And similarly for transient delay fault, right? For the transient delay fault, you remember what we just discussed here, right? The delay faults, right? Delay faults also require 2 test vectors, right? So this only says that these transitions, okay, so it is not the same. Okay, for stuck open faults, some other test vectors will be required. For delay faults, some other test vectors are required. So they are not really related. So we talked about test vectors from moving from one to other, but they are different for these two. Okay, so if you see here, this is one NAND gate simulation, and these are the output is to be good, and the stuck open faults which will be detected by these transitions is this, whereas for the delay faults, it is a different kind of delay faults. Okay, so so the number of test vectors required will be different. Okay, for both of these things, the kind of test vectors required for detecting SOP or TDF are different. Okay, and coming to the last portion is cell aware fault. Okay, so this was an 3:1 mux. Okay, so from the fab lab itself, because of they are making this many times, right? So the fab lab can give you an fault matrix. Okay, fault table, right? Said that okay, these kind of faults, transistor defect, bridge fault, open fault, transistor defect, okay, because of the statistical data which they have, because they have been manufacturing this in a mux many times, 1,000 times. From that, they can give you an probable faults for this particular cell. Okay, that is known as cell aware. So from the fab lab, right, the probable fault list is available to you. Okay, so if that is available to you, then it make like you don't have to keep catering for all the transistor faults in that case, because from the fab lab data, okay, you will say it might say, okay, the probability of a fault here is almost negligible. Okay, it has never happened in the past. 10,000 ICs we have manufactured, and hence there is no fault which would occur here. So I may not want to do that fault itself. But because of the layout issues and all, they say, okay, there is a possibility that there could be a capacity, there could be a bridging fault here. Okay, these are the normal kind of faults which are. So your fault list comes from the cell given. Okay, this fault list is given by the fab lab. Okay, so if that is available, then it actually makes our testing little faster and more realistic, right? So this says that okay, because of the cell aware fault model, right, some static and delay faults which was done, so the total number of coverage is much higher. Okay, so and the total number of test vectors also you could minimize. Okay, you can where these faults which are not likely to happen, you need not do that. Okay, so if that kind of information is available from the test lab. So there is one example out here, right? So here initially we saw that, okay, these are the test vectors stuck at fault. Okay, now if the Fab Lab says over and above this we will do as such, okay, this is minimum which we will do, okay, based on number of input lines, these are the tests which we will do. If the Fab Lab says there is a possibility of one bridging fault also here, okay, now I am not talking about because this is the only cell aware constraint which has come, additional constraint which has come, right? I am now, suppose if I have to start doing open fault here, right, all the other faults, then this test vector will become a big list. Okay, but from the Fab Lab it has come, the data has come that there is only one possibility during fabrication, that there could be a bridging fault between these two wires. Okay, and for that means this input is 0 here, so this can come here, right? So for that, if I give this particular test vector, if I give input as 0 and in1 as 0 and control as 1, and if I am getting an output as 0, okay, then yeah, if I am getting the output as 0, that means it is not a fault. But if I am getting a output as 1, okay, that means this is control, right? So this is 1 here. So this 1 is coming here because of the bridging fault. And if I am getting a 1 at the output, that means this bridging fault exists. Okay, so I can detect this bridging fault by this particular test vector. So I will introduce this additional test vector based on the input which comes from the Fab Lab, that you should cater for this additional bridging faults. Is it okay with all of you? Right? So normally in the testing domain, what we do is we just go for single stuck at faults. Okay, so all the algorithms which are there, we generally go for this, right? Or we are going to neglect the bridging faults and the transistor faults, right? And even the delay faults also for the time being, right? So we will focus on this static faults, right? But in practice, okay, there could be some Fab Labs which would be giving these additional faults. So that will come as so that the fault list, additional fault list will come from the Fab Lab. And in that case, you could go for some additional test. Okay. Otherwise, if you start doing, because statistically, what over a period of time, the stuck at fault coverage, if it is close to 100%, you can assume that more often than not, very high probability that the chip will function properly. So in the next class, what we are going to discuss is, okay, let me just give a hint of. So in the we saw about fault modeling, right? So now in today's class, now we'll also in the next class we will what we would see is, suppose there is a circuit like this. Right, there could be right, there could be a fault here, right? There could be a fault here. There could be a fault here. Okay. Now, is it possible that this fault and this fault, right, they are the same, like as far as the test vectors is concerned and the output is concerned? If I test this, automatically this also will get tested, right? Then what happens? My total fault vector, total fault set will reduce. If I am trying to find equivalence faults. Okay, this if this fault is equivalent to this fault, or this fault is equivalent to this fault, then this list gets compressed, right? And if this list is compressed, then my algorithm will run faster. Okay, I will not keep duplicating the test. Okay, trying to find this fault and trying to find this fault. So I have to first collapse the list. Okay, that is known as fault collapsing. So in the next class, we are going to learn various techniques for collapsing the faults and making this a fault list as minimum as possible. Okay, that is the first step. And once that fault list is minimized, then we will see in the subsequent classes how to go about making algorithms to detect those minimized fault list. Okay, so that's all for today. We'll meet in the next class. Unless you have some doubts, then you can ask me now. Okay, thank you.